Welcome to Equinox, where Rob and I are striking the balance between the light and the dark. This is episode 35. My name is Joseph Darnell, and I'm joined by the one doctor on the show, Robert Carter. Hello, Rob.
Hello, Joe.
I happen to be 35, and Equinox is turning 35. It's kind of special.
Wow, yeah, we got a little ways to go before we catch up to me. All right.
How are you doing, friend?
Fantastic.
Okay, good to hear.
Working hard, lots of great ideas, not enough time to do everything I need to do, which is always a good thing. You don't want to be bored when you're working.
No, I haven't been bored either. It's been a good time for work.
Yeah.
And things have been working like clockwork, really. We just had 2 very good days. You know, this is the beginning of the real wintry cycle. We've got the cold fronts. It's down into it's finally dropped down into the 30s.
Yes, woo!
In November. I love it.
Love it. Absolutely love it.
My dad shared with me a video. No, it wasn't my brother. I think it was my dad. He shared with me a video he had of a snowstorm that we had here in Georgia on this day in 2008. I did not remember that. So he had pictures taken of it, and that's what he showed me. So it was neat to be able to see those kinds of things.
I'm sure I was here. We have these periodic snowstorms. Hard to remember them all. I remember in December 2 or 3 years ago, we had 11 and a half inches the first weekend of December. And no one else had that much. It was just here. And it was like, what on earth?
Yeah.
That was really cool. But then last year we had no snow.
Nope, not at all. My wife's first Southern Georgian winter.
I hate those winters. I need 1 or 2 snows a year. That's a good Georgia winter, but 0 snows, that's very disappointing.
Oh, no, yeah. We got to have a little bit of snow. I actually am thinking about going down to Florida for part of a winter vacation, and I feel like torn because part of me also wants to go north to make sure we get some snow.
Yeah, it's kind of sad to spend the winter in Florida. All you Florida people, you're like, oh, you're laughing at us how cold it is, but you know what? I don't like the heat. I need to recharge in the winter. What I pretend is I'll take a late winter day and I'll pretend I'm sucking a bunch of cold into an inner pocket inside my body. And I said, okay, sometime in August, I'm going to open this pocket up and I'll cool myself down and say, oh, winter's coming.
Exactly. I'm going to do that too now.
Cool. I mean, looking at my ancestry, right?
Yeah.
I mean, I come from southern Norway, northernmost Germany, England, northern Ireland, and the northern Netherlands, like all these countries surrounding the North Sea.
It's in your blood.
This is what I'm bred for. I don't do Georgia summers.
No, me neither. What are we doing here? We need to migrate.
No, man, because I don't really like New York winters either.
No. I was born in Virginia. I could handle that. My wife's from North Carolina. My mom's from North Carolina, and my wife is from Oregon, so she doesn't have a whole lot of experience with snow where she was from. It mostly just rained.
A couple winters ago, CMI sent me up to Chicago in February. I had never seen 17 degrees below zero.
Oh, ow.
And then I went north into Wisconsin on the lake in Wisconsin. It was 22 below. And after an event, we did 3 events at this one church, and every day fewer and fewer people came. And I mentioned it to the pastor, and he goes, yeah, this many days, this cold, no one can start their car anymore.
Oh.
So you might get, the first day you can start your car. Second day, maybe. Third day, your battery doesn't work.
Wow.
Yeah, so I'm glad I don't live up there.
Yeah.
You just freeze, that's all. In fact, the door of the van, we opened it up, the sliding door, opened it up, loaded the books, and we couldn't shut the door. It froze open.
No. Oh, wow.
And so we had to drive, and we finally broke it, and we could close it, but it wouldn't latch. And you can't throw water on it to melt the ice because then it's just going to freeze up. So we cranked up the heat, drove for about 10 minutes with this 20-degree below zero wind whipping through the car. And then we tried it again. We finally got it to latch. And then we got up on the interstate and went home.
Whew.
Cold, man. So you people from up north listening, you know what we're talking about. All you people in Siberia, may God bless you this winter to stay warm and toasty. Joe, get our conversation away from freezing cold stuff to something more appropriate to what we'll.
Yeah, so let's electrify the conversation and warm up again.
Ooh, all right.
Let's go ahead and just go into our main topic, shall we?
Okay.
There's nothing else to talk about. I mean, nothing else in the world is going on. It's not like we're ignoring the elections as we're recording.
Oh, dude, I've got about 3 tabs open that I am not going to look at because we started recording at 7:30 in the evening and polls in Georgia close at 7. I am sure by the time we're done, most precincts will have recorded. And this is like the sword of Damocles hanging over my head. And I was like, all I want to do is click and look, but I'm not going to let myself
do it
because it'll be totally distracting. And I might be completely depressed for the rest of the thing. So no, I'm focusing here on Equinox and that's it.
Okay, good. So everybody, if you're listening to this, I hope you're not looking at the elections. Turn off Twitter, close those browsers.
Well,
listen to us.
They can't.
Yeah, I know. I know,
they can't because this won't be.
But they're probably following up on the commentary about the elections. They need to get that out of their head. Stop thinking about the elections and who won just long enough to enjoy the next hour with us, okay? Okay.
Even a couple of days from now, when we release this episode, half the country will still be depressed.
Yeah, we're here for you. We love you. And
that's right.
We're here for your support.
Let us distract you for a little while.
So you wanted to continue with the conversation we began last week about electronics, picking up about how does electricity work and magnetic fields. And I saw the wheels going off in your head when we were thinking about this idea, that it just sparked all these good ideas for this discussion. How I kind of feel like we came upon this backwards. We talked about the end result of electronics first. And then we started to realize, and you started to realize, we hadn't explained how the fundamentals of electronics and magnetic fields work. And
this is very true.
I know you have a lot to say, and maybe to just tease people before you get into where you want to start. I was thinking about this as I was listening to, another podcast that I was working on earlier today. So I was doing this study on the eclipses. And it was describing the behavior of the sun.
I saw that had been released. I haven't listened to it yet.
Okay. So on the article in this podcast about the eclipses, one of the things he was talking about was the chromosphere and the corona of the sun.
Yep.
And okay, so the outer area is the hot one, right? Hotter than the surface of the sun? Or is it deeper down?
No, it's deep down. It's very, very, very hot. But the outermost stuff, the thin material way on the outside edge, is extremely hot.
Right.
And before the Parker Solar Probe, we didn't know why. Now, the Parker Solar Probe was a satellite with a giant heat shield in front of it, and it was designed to, in a very elliptical orbit, approach the sun and fly away and cool off again. And then approach the sun, and it went through that hot thing. And I know they were testing stuff. And honestly, I haven't followed up on it. I don't know what the result was. I don't know if anyone figured it out. That was a couple of months ago.
Oh, interesting.
So something to look up. Parker Solar Probe.
But the point is that they found that the outermost area was a whole lot hotter than, and it was like the radiating heat of the area, if I understand right, that it is hotter than even the surface. Is that true?
This is very true.
Wow.
Much hotter. Well, it's the same as true in Earth's atmosphere.
Okay. It's hotter on the edges of the atmosphere?
The place that the International Space Station flies through is extremely hot.
Oh, huh.
But because the atoms are so dispersed, I mean, think about it, only a really hot atom could fly that high above the Earth. Cooler ones won't move as fast.
Yeah.
But because they're so far dispersed, there's almost no heat transfer.
Okay.
That makes sense?
I get it then, yeah.
So you can still have a radiator on the International Space Stations radiating heat out into space, even though it's a lot hotter theoretically in space, then that radiator should go the other direction. It's just a weird thing that temperature is the average molecular motion, but it depends on how far apart the atoms are for actually how much heat you would absorb.
Yeah, I wouldn't have thought of it that way because we don't think of heat that way here on the ground level. Interesting.
No. Well, if you got in a pool, if you got in a 110 degree hot tub, you would die much more quickly than if you're outside on a 110 degree day. Now, of course, there's sweat. Okay, I got that. That's probably the difference. But there's also this thing about heat transfer in water versus air. It's a huge difference. Huge difference.
Yeah.
Which is why you would freeze to death in water much more quickly than you would freeze to death on a cold day.
Okay. Yeah, that makes total sense then. Yeah, I get that.
Okay.
So what they were saying is that in the podcast I was working on is that the sun's magnetic field is why that outermost area is the hottest one. And I realized I don't understand magnetic fields.
Oh, that's where this is going.
Yeah.
Sorry, it's a long detour before we finally got to that point.
No, it's okay. You're a scientist. It's easy to get off on things.
It sure is. I'm going to tell you that I don't understand magnetic fields either, even though I've been thinking about them for decades.
Okay, so being lost in the dark has company.
Yes. Magnetism is one of those fundamental forces of the universe. So in one sense, we just accept it as is.
But then on the other hand, it's also like, well, why do we accept it as is? Because it's highly complex, but how does it even work and why does it work?
Yeah, there might be people who have a better answer to what magnetism is and why, but it's like gravity. It just is. It's like electric charge. It just is. These are the fundamental forces in the universe that might not have an explanation. They might. Maybe someone out there has a good explanation. I certainly don't have one. So we study these things and we manipulate them and we use them all the time. But we really don't know what we're doing. We're just copying an effect that we discovered. Oh, this does that. Okay, why?
Right.
Oh, I don't know, but I can make a radio.
Yeah.
I can charge my iPhone by just putting on a plate. I don't even have to plug it in. I can just put it on this thing here, and my iPhone will just charge. Ha ha ha.
Yeah, and they're going one step farther than that. Now you got these Qi chargers with magnets in them and magnets in the back of the phone so that your Qi charger can snap into place. And even though it was wireless charging before, now it's magnetic wireless charging. And that's the new hotness.
Yes, and we will explain on this episode how that works.
Excellent.
But I don't still know what magnetism actually is.
So, okay. Well, then let's not begin there. Let's back up and let's take it from the top of the outline. You wanted to go back into our time, back into equinox history.
Episode 1. For all you faithful listeners out there, you will remember episode 1, the greatest theory ever. And we talked about gravity and how gravity theory, or Newton's law of gravity, is a single greatest episode of scientific prediction ever in human history.
I seem to remember you saying something like that.
Okay. Well, now I want to go towards a sort of like a one ring to rule them all effect. It's not the same thing as gravity. It is amazing in itself, but it is the one force in the universe that controls the world in which we live. In the 1700s, it did nothing. There was nothing in this realm that had any impact on human life whatsoever. But today, everything is dependent upon this one discovery from the 1820s.
Huh.
It was actually a Danish scientist named Oersted, Oersted. There's a bit of a controversy whether he did this by accident or whether it was planned. We know he was thinking along these lines already, but no one had any backing up for the ideas at all. But he was in a lecture hall at his university in Denmark, and he connected a battery to a wire, maybe to power a light or something. But point is, there was electric current running through a wire. It was like 12 volts or something like that. And nearby was a magnetic compass pointing north. And when he connected the wire out of the corner of his eye, he saw the compass move. And he said, oh my, there is a relationship between electricity and magnetism.
Wow, okay. So well, help me understand then. How would it seems awkward that we had batteries and we were powering electronics, but we still didn't realize there was any magnetism involved. Was it just because we
had no idea.
Didn't anticipate that? They were they not using magnets for anything back then to put on the refrigerator?
Sure they were.
Nothing like that? Oh,
sure. Okay. Yeah, they had magnets. They had natural magnets, lodestone, magnets. They weren't manufacturing magnets yet. They were very soon going to start manufacturing magnets using electricity, but they were natural magnets, and it was a mystery. The Greeks had lodestones. Some of the Greek mystery religions, they would levitate things. Ooh, look at the magic power! Oh, and well, no, it was actually just a meteorite or something like that that was magnetic that they would use.
Oh.
Anyway, they had magnets. They had electricity. Nobody knew that these things were the same. Nobody knew that there was going to be this thing called electromagnetic, and it changed the world.
Okay, so then you're not just going to try to explain electricity and magnetism, but also electromagnetism.
I'm going to try to explain how the relationship between electricity and magnetism drives almost everything in our modern society.
Yeah, we may not be able to understand politics today, but hopefully we can understand magnetism, electrons, and yeah.
Yes. Just a couple of years later, in 1826, Ampere, a French scientist, he comes out with what we now call Ampere's law. It's real simple. The strength of the magnetic field is proportional to the amount of current going through the wire. More current, stronger magnetic field. It sounds like duh, but back then that was a big deal. He quantified it and he put numbers on it. So he said, if you want a magnetic field of this strength, here's how much current you must have. We also found out really quickly that magnetism generated through electricity penetrated glass and wood. It was a magic force that went through other things.
It really is amazing, even to this day. I don't think
Strange.
there are very few properties in nature that are as cool as magnetism. It is always cool, timeless cool.
Always cool. But the fact that a battery-powered device or any electricity running through a wire produces the same thing that this black thing stuck to my refrigerator produces. What?
Yeah.
That's literally the thought that must have gone through a million people's heads. A couple years later, 1831, another famous scientist, this guy's English, Faraday, he comes up with the law of induction. And that is where the conversation starts. He clinched it. He realized that not only do flowing electrons make a magnetic field, but a changing magnetic field will move electrons.
Oh,
now
okay,
we have the basis of an electrical generator, the basis for radio transmission and reception on an antenna, etc.
It's really marvelous that the electricity goes out of where it originated and can travel great distances to arrive at its destination. Pretty much without, I don't want to say, I don't want to trivialize and make it sound ridiculous or like magic, but it's just amazing that electricity can travel great spans and that we can count on it every time, that it's not going to go back the other direction or there's not going to be an overload. It's very predictable.
It does go back the other direction. It goes forwards and backwards 120 times a second. Or 60 times a second. But see, that's the big war between Tesla and Edison. Edison wanted direct current electricity, like from a battery, direct current, not alternating current like in our plugs. But the thing is, you can't send a lot of electrons through a wire with direct current. The wire starts to get really hot. So yeah, you could have a 12-volt system, fine. You couldn't have a 60-volt or 120-volt like we have. And so Edison's initial powering, I think New York City, I think he did a couple square blocks for some rich people. It was okay. But then Tesla goes and builds a generating system at Niagara Falls, and he powers the entire town of Niagara Falls with alternating current. And everyone's like, alternating current's dangerous. It'll kill people. Well, yeah, okay. It's more dangerous. That's why we have high tension wires up in the air. And we step it down to 200-something volts, and it comes into your house. Then you split that. The 200-something volts goes to maybe your stove and your washing machine, or the stove and your dryer. And then 110 goes to all of our other appliances. And it works great. See, the reason why alternating current is wonderful for high voltage transmission is because the electrons actually don't move. They just wiggle back and forth because it goes forward and backwards, forward and backwards, forward and backwards. They're just wiggling back and forth. And most of the time is not spent at the highest current flow. It's a sine wave with a peak, high current, zero. High current in the other direction, 0. High current in forward direction, 0. High current in the backwards direction, 0. The sine wave. So most of the time,
Did you say the sine wave or the sound wave?
sine,
Okay.
S-I-N-E, sine wave. It's the electricity is not really moving in the wire. It's just wiggling back and forth. And most of the time is not spent at peak voltage, which means there's not a lot of power loss. The lines don't heat up. For direct current, if you want to power a whole bunch of things, you got to start electricity at one end, send it through the wire, and more electrons have to flow through that wire to get to whatever device is being powered. And it's wasteful. The line gets really hot, and it's extremely limited in how much power it can deliver. So Tesla, we should do a show just on Tesla.
Oh, please.
Mad genius of all time, died penniless. He changed the world, even probably more than Edison did. Hard to say that, but anyway. So we have this idea of induction, and that is moving. I'm going to say changing electric fields can create a changing magnetic field, which can induce current in another wire. If you just had a steady electric current, you have a static magnetic field. If you have a wire living right next to it, just sitting right next to it, nothing happens. But if you turn off the electricity, the magnetic field collapses, and that induces a current in the other wire. If you turn on the electricity, the magnetic field grows to maximum, and as it's growing, that induces a current in the other wire.
Okay.
So you can send electricity across the air via magnetism to another circuit.
Right.
That right there is the radio.
Oh, okay.
And a lot of other things. We also have this amazing device called the transformer. First one was invented about 1885-ish. No one's really exactly certain. Nikola Tesla did patent a particular transformer. And a lot of people say, oh, he invented the transformer. No. It had already been invented. He invented a transformer that can step up to extremely high voltages, which gave us the Tesla coil.
Oh, okay.
You know the plasma balls where you put your hand on it, it goes bzzz, bzzz,
Yeah.
It makes that like purplish thing. That's a Tesla coil on the inside, just a very weak one.
Yeah.
But you can make
love
Tesla coils that can send lightning sparks like 50 feet using his transformer. And so let me explain the transformer, and I think this will probably help us to understand this law of induction.
Okay.
If you first, let's explain an electromagnet. So current running through a wire makes a magnetic field.
Okay. Yeah.
Now, using the classic right-hand rule, if you use your thumb and point that in the direction of the electron flow, your fingers will wrap in a circle around the wire. That's the direction of the magnetic field. It's a circle around the wire.
Yeah. Yeah.
If you take that wire and coil it, and then lay it in front of you, left to right. Well, on the top of the coil, the electricity is always flowing away from you, let's say. And the bottom of the coil, the electricity is always flowing toward you. Well, using the right-hand rule along the coil, all the norths are all pointing in the same direction, and all the souths are all pointing in the same direction. And you now have a magnet. Now, the wire is a magnet, fine, but a very weak one. Every time you wrap it against itself and make a coil, your magnetic field strength 1, and then 2, and then 3, and then 4, and then 5, you just keep on adding more coils, and the magnetic field gets stronger and stronger in your electromagnet. That make sense?
Yes. Yes.
Okay.
I'm actually like visualizing it right here in my over my hand on the desk.
Cool. Because we all did this in like 7th grade science.
Mm-hmm.
Classic 7th, 8th grade stuff. Okay. Take that electromagnet and put it on a ring of iron. Only like make it usually they're squares. It's a square donut of iron, maybe as thick as your pinky or your thumb. And so this iron bar has been bent around and welded together into a square shape, and there's a hole in the middle of it. Well, take one flat side of that and do a bunch of coils of wire. Now, the wire is insulated, so the wire doesn't touch the iron. But because the electricity flowing through that wire will induce a current in the iron, if you wrap another coil around the other side, you can transfer electricity from one circuit to another, even though the circuits aren't connected.
Wow.
Because the changing electric field would induce a magnetic field in the iron, and the changing magnetic field in the iron will induce an electric current in the other coil. They're reversible. Now, there's energy loss here, but they can design transformers that are like 99% efficient or something like that. They don't lose a lot of electricity. And here's the cool thing. If you do 100 wraps around one side and 100 wraps around the other side, if you send in 110 volts on one side, you'll get 110 volts out the other side.
Sure.
But if you do a different ratio, maybe 100 on one side and 1,000 on the other side, or 10 on the other side, you're going to have a step up or a step down transformer. You can change the voltage. Now, the power has to be the same. You can't, the amps flowing through this, you can't get more power out, but the voltage can change. And so you plug in this little white thing into your power strip and you plug it into your phone. The power strip's 110 volts. That the wire going to your phone is not. It's only a few volts. Why? Well, actually, it's basically the electronic equivalent of a transformer. The old days, it would have been a straight up transformer. Like my model railroad had 12 volts coming out, even though I plugged into the wall and I plugged in and go hum. It would always hum.
Yeah,
I love that hum. That's 60 hertz hum. Hey boys, hear that? I'm sorry, I was trying to do Apocalypse Now impersonation about the napalm, but anyway, you hear that sound? That's the 60 hertz sound. And I said, cut that out. That's terrible. That's awful. That's not even funny. Anyway, my old model train transformer would go from 110 volts to 12 volts and had a variable resistor, so I could go from 0 volts to 12 volts by turning this dial. And it was just literally, if I opened that thing up, I would see a bunch of coiled wire, and it might be convoluted because modern ones, they're not real simple. But if I could figure out where the wires go, I would see that there's a whole bunch of twists of wire on one side of a metal donut thing and some other wires on the other side that had a different number of twists, and it'd be a step down going from 110 to 12 volts. Cool.
Mm-hmm. Okay.
All right.
That's not intuitive. I mean, that sounds like another kind of thing that they would have happened across and realized only after the fact with experimentation. This is the way it works. Would you say?
Well, Faraday's law of induction, the next step is, I can make a transformer. And they're building transformers within a couple of decades.
Ah, okay.
So they didn't need them right away. They didn't really have an application for current yet. There was no need for a transformer until someone says, I want an electric device. I can produce some electric power. I don't want that power. I want this power. Well, let's just put something in between to convert it from what I can produce to what you want. And now we had the ability to provide a standard electrification on a grid, and anyone could build a consumer device that could use any voltage that they want by simply using a transformer. Cool, huh?
Yeah, awesome. I didn't realize that the transformers were the key component.
Oh, absolutely key component. Absolutely, 100% absolutely. Now, modern equipment, they use diodes because diodes only let electricity flow in one direction. If you put a diode on an alternating current line, it'll chop out half the signal. Like if alternating current goes forward and backwards, forwards and backwards, it's only going to go forward, forward, forward. You lose half your signal. But if you put two diodes in opposite directions, it won't block anything. But the electricity will always flow in the same direction. And a bridge rectifier, there's 4 diodes in a diamond pattern. And if you put that on an AC line, it'll convert it into direct current. And then you have to change the voltage. They use usually other things other than transformers, other little electronic gizmos that'll change voltage now. But it's the same basic idea. All right, so we are listening to each other talk on speakers, right?
Yes.
Okay.
They're connecting to, well, I mean, in my case, I'm not even wired. I'm hearing you over earbuds.
Oh, even better. So I'm wearing a headset with a mic, and I'm plugged into my computer. So I speak into the air. The air vibrates. That vibration is picked up by a microphone. All sorts of different microphones. They used to be carbon. Now they can be all sorts of different ways to pick up sound. But all of them have one thing in common. The sound waves produce a physical movement of something that changes the voltage on a wire. And the voltage change depends upon the frequency of sound and the amplitude of the sound. I mean, you can see the waveform on Audacity as we're recording. That's my voice.
Yeah.
And that wobbly thing, the closer they are together, the higher my voice is, and the farther apart they are, the lower my voice is. And then as I talk louder or I talk slower, the amplitude changes. Well, that's an electronic circuit converting sound waves into electricity. That goes through a wire. That wire eventually gets to your computer. Now, if you were plugged in, the electricity would go up to your speakers and run through an electromagnet. And inside the electromagnet is another magnet just suspended in space that's attached to, like an old speaker, it'd be a magnet on the back of a piece of paper, a paper cone. And as that oscillating signal in the wire was running through the electromagnet, it would be creating an oscillating magnetic field, which would wobble the magnet, which would move the paper cone, which would produce a sound that propagates through the air. So the law of induction is right there in every speaker that we hear things.
Huh. Yeah. Well, see, that's the thing is about all of these examples with electronics that you've got ultimately digital picture, you've got digital sound, you're transferring digital information, you're transferring power, and it's overwhelming all the various components you have that can pull off everything from sound and visuals. Like, I'm using a really slim computer. I'm looking at your waveforms right now, and if you don't know what waveforms are, guys, you can just look down at your cover art and on your phone while you're listening to this podcast. I'm going to put some waveforms on the cover art for this chapter.
Oh, cool. Good idea.
So that you understand, like, one set of the waveforms are Rob's and one set of the waveforms are mine. And those are the electronic signals that Rob's describing. And it's weird because we also have the visual, because those are the electrical impulses, but also the sound is represented, but also a visual representation of them.
Yeah. But what happens when that signal gets to your side? You're not wired to your computer. How does the signal get to your earbuds? Well, are your earbuds Bluetooth?
Yes.
Okay. They don't have to be Bluetooth. They could actually have a different antenna system. There's all sorts of ways to propagate a radio wave, but Bluetooth is essentially a radio wave. It doesn't go very far because of the frequency, but your computer has a little antenna that propagates Bluetooth frequencies. The electricity runs through that antenna. Well, the waveform runs through the antenna, and because moving electric charges produce a magnetic field, the magnetic field varies because the electric charges in the wire vary, and they vary according to the waveform. And now you have a radio wave. Magnetism. Light and magnetism are interrelated to one another. If we can make a radio wave with magnetism, that means light and magnetism are the same thing. That means when we see things, we're seeing magnetism. We're also seeing light. They propagate at right angles to one another. I don't quite understand why that's a mystery to me, but they propagate at right angles to each other, but you always have magnetism, and it's the electromagnetic spectrum. Light is magnetism. Magnetism is light in one perverse way of thinking.
Huh. Yeah.
Complicated. It's probably not true to say it that way, but they go together all the time. So by making this oscillating magnetic field, it makes a radio wave, which is light, and that's picked up by an antenna in your earbuds. The cool thing about antennas is that if you had an antenna at the same length as the wavelength of the signal, it will pick it up very well. Make it a little shorter or a little longer, it won't pick it up as well, because an antenna tuned to a specific frequency, the electrons in the antenna, as that magnetic field hits the antenna, it's going to induce an oscillating electric field in that wire. And if the wire is the right length, it'll be perfectly in tune. Just like when you ever gone into a cathedral and hear someone singing, or someone rubbing their finger on top of a wine glass.
Yeah. Yeah, that one's especially
That's a resonating frequency. Now, if you go too fast or too slow, it doesn't work, but just the right speed, boop, you hear that sound? Mm-hmm. It's a resonating frequency. Well, if you get the resonating frequency of the wire, you have the optimal signal strength. You can make it a little shorter and a little longer, get it a little off tune, but you could still pick up that signal, but it will be weaker. And so, remember the old cars where we had the line in the windshield?
I'm thinking about it.
Started at the
was this
that little thin wire that it went like two eyebrows. It went up and then across the top of the windshield.
Yeah, I remember that now.
Okay.
Mhm.
Well, why is it that length? That's your antenna for your radio. Why is it that length?
I
Because a
don't know.
wire of that length, which is a couple of feet long,
Yeah.
optimally picks up radio waves, which are measured in meters.
Oh, okay. Ah, that makes a lot of sense.
Oh yeah. So if a wire that's exactly the same length as the wavelength of the incoming transmission is optimal, a wire at 1/2 the length will work just as well because of harmonics.
Oh, interesting.
It picks up exactly 1/2 of the wave. And most of the antennas that we use are 1/2 the wavelength. Because why we use a big wire? Let's use a short one. And so you can actually judge the frequency of the incoming light just by looking at the size of the antenna. Have you ever seen a Yagi antenna?
No. Or if I did, I didn't know it was Yaggying on me.
Oh, okay. You probably have seen them and didn't realize it. It's an antenna. It's basically a straight bar, and then along that straight bar are, depends on the antenna, maybe 3 or maybe 8 bars of exactly the same length in parallel down the length of that antenna.
So it would be like several wires all held together.
Right angles to the main wire, yeah.
Okay.
And it's a directional antenna. They point it at where you want to go. Now, it doesn't go forever, but I've done some work on like sewer pump stations. When I was in Miami at an engineering firm, we were doing this sewer study of the city of West Miami, and all the pump stations had a Yagi antenna. A mast goes up, and this antenna is at right angles, horizontal to the ground, and it was pointed at the main sewer station. So they could pick up the signals from all the pump stations, know when the pump turns on and when the pump turns off. Everywhere I drive, every time I see one of them in a neighborhood, I know that there's a sewer pump station right there. It just your eyes just kind of pick it up now. My eyes do. But this antenna is weird because all of the little antenna things are the same length because they're designed to optimally produce a single frequency.
Well,
cool,
interesting.
huh?
Okay, yeah. I'm on board with
Okay.
that. The funny thing about you're talking about antennas of radio and frequency. How much would you say is still dependent on radio frequency in our day and age? Because I think that in layman's terms, we're thinking about AM and FM. Is that also the same sort of thing that we're getting Bluetooth from?
Hold on a second.
Yeah, like how would you explain the
Bluetooth
difference between radio and
frequency range? Oh, 2.4 gigahertz. That sounds very familiar. Okay, wait. I'm going to say wavelength 2.4 GHz. Yeah, of course. 12.5 centimeters. Wait a minute. We talked about 12.5 centimeters recently, didn't we? You remember the microwave oven discussion?
Yes, the holes on it, and the microwave waves can't get through it.
Yeah, it's 2.45 gigahertz. It's the same frequency.
Oh wow, okay, huh?
And so you're actually cooking your head when you got your Bluetooth on. No, I'm kidding. It's such low power, it does nothing. And very short wavelength, but it's 12.5 centimeters. That's the wavelength. So your earbuds need an antenna about 12.5 centimeters or 6.25 centimeters, only half a wavelength. It might be a quarter wavelength. You can do that too. And it doesn't have to be straight. It can be coiled up. It probably uses some electronic circuit, not just a straight up antenna anymore. There's all sorts of ways to make antennas that are weird to me. I'm not an antenna design specialist, and they get very strange very quickly. But that's the basic idea, is the law of induction. That microwave frequency signal is inducing an electric current in a antenna, which produces, and that electric current is then run through a coil, which then wiggles something that creates sound that you're hearing.
Wow. Okay. Yeah.
Okay, remember the GPS discussion just last week?
Yep.
So GPS satellite produces a signal. It propagates through space. It hits the atmosphere at a very clear frequency where there's very, very little atmospheric attenuation. And it reaches our phones. That phone has an antenna, and it induces a current in the antenna. And the current is able to say, I am GPS satellite number 52. I am exactly over Bandar Seri Begawan. That's a real city. And it's capital of Brunei. And it is exactly 12 minutes and 30 billionths of a second now.
Right.
And all that information is relayed digitally through the air to the antenna, which then the computer on your phone picks up. I guess it's probably a GPS chip, I imagine, on the phone. And it translates all that, and it tells the phone exactly where it is in the world because of the law of induction.
Wow.
Metal detectors. Metal detectors work because there's a magnetic field, a magnetic electromagnetic field, and that thing that you wave across the ground, and when it goes across something metal, it interferes with the magnetic field and changes the frequency of something, so you hear beep, 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 boop, sort of funny sounds. You know when you drive up the traffic light that's red, and you have to wait for it to turn, and all of a sudden it's green, and you can go through the light.
Uh-huh.
How does it know that you're there?
Okay, I'm going to feel really dumb if I'm wrong about this, but I was thinking that it was something about weight on a spot on the road.
Nope. Nothing to do with weight at all. And it's not a camera.
Bummer.
Just look at the ground and the intersection. You'll see it's like someone sliced the tar.
Yeah, and so I thought that there was some sort of like way that it would feel the weight of your vehicle over that spot.
Nope. There's a wire there. It's a metal detector.
Oh, wow.
There's a current running through the wire, and your car induces a change in the current because of the metal in the car. If you had a plastic car, it wouldn't work. I've seen guys riding bicycles, when they get up to an intersection, they'll get off their bike and lay it on the ground.
Nice.
Because the bike frame is enough to trigger the signal, and they'll change the light. And some lights, there'll be a pad right at the white stripe, and then behind it be another pad. So you need at least 2 cars there before the light will trigger. And some of them, there'll be a space between the 2 pads, so you need 3 cars there for the light to trigger. And when I see that, knowing what's going on, I'll stop with a very big gap between me and the first car. So he's over the first sensor and I'm over the second sensor, and it'll trip even though there's only 2 cars present. Because I'm a nerd like that, you know. So traffic light detectors, metal detectors, GPS, radio, Bluetooth, antenna. There's a problem also with circuit boards. We want really fast computers, but if we send a lot of electrons through wires on a circuit board, they're going to start producing radio frequency signals. They're going to start producing electromagnetism and things like that. We have to be very careful when we're designing modern circuit boards to keep the wires as short as possible and to make sure there's no interference from one wire to another. Because you send a signal down one wire, it can induce a current in another wire. That has to be factored in when we design computers, or computers would not work. It would be a disaster. There's also this really cool thing called impedance. If you run electricity through a coil, the coil will start to develop a magnetic field. But a changing magnetic field induces a current in the wire. It actually induces a reverse current. It slows down the electricity going through the coil until it reaches full strength, at which time that effect stops. And then when you turn off the electricity will keep on flowing through the coil. Even though the circuit's off, the collapsing magnetic field will induce a current in the wire itself in the forward direction. So you've probably in the workshop, right? You turn on a circular saw or a band saw or something with a big motor. It doesn't instantly turn on.
Right.
It has to ramp up a little bit. That's because the coils in the motor are resisting being turned because of a self-induced reverse flow of electricity as the magnetic field in the coil is building up.
Interesting. Wow.
You can also therefore use a coil to chop out sound waves in a wire. You could use it as a choke or a filter. if a coil it has a certain frequency of ramping up and ramping down, that means it'll blot out certain frequencies. Other frequencies will sail right through it. So you have a bandpass filter. Now, modern days, we just take a soundboard and slide these things up and down. The old days, they'd plug literally a coil into the wire, and it would chop out some of the frequency of the electricity going through the wire that was then going to a speaker and would change how it sounded. This is cool. I mean, this has so many applications. There's an unending number of applications.
What kind of blows my mind is that it's all very knowable and consistent. And I remember one thing that was explained to me from a friend that interned with Apple in California many, many years ago. He worked on the team engineering batteries for the iPod back when they were still making those. And he was explaining that the main objective was to get that thing to not be too hot and still do its job and be an efficient battery.
Yep.
But the thing is that they had a team and they could make an advancement, they could work it out, and with a scientific approach. And in the end, you have just this product that, it's not that it seems like it's magical that it's able to power and be consistent, but it's amazing that this stuff is knowable and calculatable and repeatable. So much so that you can get it to work hundreds of thousands of times for pocketable devices.
Yeah, because science is predictable. Operational science is amazing. And the same brains that were figuring this out in the 1800s are figuring out how to make iPods and all sorts of Apple devices and PC devices today. Just stepwise, one thing after another after another. Oh, if I do this, and I can do that. If I make this wire a little shorter, it uses a little bit less power and it gets a little bit less hot. Right. Oh, if I do this here, it does that. And just these incremental changes over the last 150 or more years using the same idea, this very simple idea of induction, has led to everything in our modern society.
That's really awesome.
And I don't think the people in the 1830s would have any idea of what was coming. What we'd be able to do with this idea that, hey, if I do this in a coil, this magnetic compass next to the coil wiggles a little bit. Ooh, wow.
Right.
And now we're able to communicate with the Voyager probes that have left the solar system using that exact idea. We're able to use Bluetooth using that exact idea. Wi-Fi, radio, upcoming 5G signals, same idea. It's all the same stuff.
Incredible. It does not come across that way.
Yeah, it sounds like all sorts of miscellaneous random ideas that aren't interconnected, but they're all very connected. I want to wrap up with one thing. Power strips.
Oh, fun. Yeah. Let's hear that one.
Plug a power strip in the wall. There's some power strips. They're just strips of plugs. They don't do any line conditioning at all. Usually the white ones, and at the end, it's like, maybe it's brown, but there's like two plugs on one side and one plug on the other side. And sometimes that plate that you put on the two-prong thing, and it makes 6 plugs instead of 2. That's just a power strip. Now, people are interchanging that with a surge suppressor. We call surge suppressors power strips, even though they're not. A surge suppressor can be any number of different things. One of them will just have a circuit breaker. So if the electricity gets too high, it'll trip the circuit and turn off power to anything that's plugged into it. Another version, I'm going to call that a line conditioner, a true line conditioner. It has a capacitor and an inductor. Now, inductor is a coil. A coil of wire has a predictable ramp up time for maximum magnetic field strength and a predictable ramp down time to zero field strength. And by attaching an inductor and a capacitor together, capacitor will store electricity. You can actually chop out all the noise in the wire. So if there's a spike that goes all of a sudden to 300 volts, even if it's really short, it can't go through the coil. It is blocked. And so you have a line conditioner. Makes a nice, easy waveform of your incoming electricity, which could be quite noisy depending upon how far you are from the power station, what might be touching the wires, like a tree branch or something like that, and what power station you're actually getting electricity from, and things like that. So just because you have something plugged into the wall doesn't mean you should plug your computer into it. but you should at least have a surge protector that'll trip. And if you're real good, and don't you have one of these somewhere? A big heavy metal box? Yeah. What is that thing?
It is a battery backup and surge protector.
Yes.
It's got a master on it.
Yes.
It's the works.
Yes. And I'm sure it's also a line conditioner that cleans up the signal for the electricity. And that's the bomb. That's what you would want, but they're expensive and they're heavy.
Right.
It's probably heavy because it's got a giant coil of wire in it, maybe 2. My dad, before he retired, he's an industrial engineer, and he forever most of his career he made tape measures.
Yeah.
And so I actually worked at this tape measure factory for several summers, and it's just
really?
I mean, a lot of grueling, hard but fun work. Just amazing watching things being produced. And his last job after they moved to Florida before he retired was working at a speaker coil manufacturing plant. And if you've ever driven a Ford car that has Bose speakers in it, his factory was making those speaker coils.
Oh, nice. Huh.
I think the company's still in existence, but they don't make much anymore because they figured out that they could get a finished product from China cheaper than they could buy the copper wire.
Oh, wow.
So they started becoming an import company, but they were still doing piecemeal work, like some electrical engineer, some experimenter, or something that's not going to make 1 million units. They need a couple hundred or a couple thousand. They would say literally, I need a 16 gauge wire with 5 1/4 turns spaced 1/8 of an inch apart. I need 100 of those.
Oh, wow.
Why would someone do that? Because they know exactly what happens when they run electricity of a certain frequency through that coil. They know how long it will take to build up the magnetic field, how long the magnetic field will take to collapse after they turn off the power. And inductors are used in just about all electronic circuits. You've probably, if you've ever opened up a power supply for a computer, you've seen a coil of wire that it was kind of like just a few turns of a thick wire. What is that thing? It's one of these line conditioner, inductor, capacitor related things that they know exactly what's going to happen to the electricity running through that thing right there. And it's exactly designed to do exactly what they need for the electronic needs of that particular circuit. And every circuit will have them, and they're all different. They'll literally tune them. In fact, at Georgia Tech in physics class, I mean, everyone learned the RLC circuit, the resistor, inductor, capacitor circuit. And you can combine them in different ways, and they have a frequency. Like if you run electricity into it, it'll have a ramp up time, and then it'll flow. If you turn the electricity off, it'll have a ramp down time, and you had to actually calculate the frequency of that circuit. And they throw all the different capacitors, resistors, and inductors in there. And it's just one of the classic electrical engineering problems that any student at Georgia Tech who's had Georgia Tech physics, and definitely any electrical engineer has studied RLC circuits.
Oh, wow.
And the idea goes back to 1821.
Nice. And things that we can learn from historical moments.
Yes. So that was my summary, not of the greatest theory ever.
No.
But of the greatest effect that rules our world.
Nice.
Faraday's law of induction.
The greatest effect ever.
Yes.
Awesome. So thank you so much for joining us on our request. If you found this episode interesting in any way, consider sharing it with a friend or a family member. And if you want to dig deeper into these topics, you can find everything that we discussed in links in the show notes on our website, also with this podcast in your podcast player. But if you want to get to the website, that is nightowl.fm/equinox/35. The show notes are also available, actually, like I said, already on your phone. You should also check out biblicalgenetics.com. This is Rob's other project. Biblical Genetics is also available on Facebook and YouTube, where you can watch the videos and you can join him in the comments. And if you want to find me, I'm at JCS Darnell on Twitter, or take a listen to my other podcast, Hi-Fi, which is available on nightowl.fm/hi-fi. Until next time, goodbye, Rob.
Goodbye, Joe.
You have been listening to Equinox. If people decided to just stop believing in magnetism, would a magnet die? Oh.